start to talk about a new topic, which is the velocity, force, and Jacobian. Okay, so from the forward and inverse kinematics, we have solved the two questions. So now we extend from position to velocity and force so that we're able to not only calculate the position of the tools, we will also be able to calculate the velocity and the force of the tooling of the end effectors. Okay, so then let's extend the questions for velocity. So now for velocity, we're answering two questions, and one is relevant to forward kinematics. That is, how fast will the tool point move given joint velocity? It's like we already know the joint variables, and then what is the tool velocity? Okay, and then the second question is, now we know the desired, which is the task velocity of the tool, and then we go back to calculate the joint velocity. Okay, so the question is, how fast should each motor turn to achieve a desired tool point velocity? Okay, so this question is relevant to inverse kinematics. Okay, so now before we start to talk about the calculation, so let me start with some concept so that it's easier to understand the following questions. Okay, so then let's start with the basic concept of velocity. So we talk about velocity, and when we learned that before, so velocity for a single point, what does it mean? Okay, so for example, let's see a translational motion. For a translational joint, so let me draw this way. So here we have a prismatic joint, and you may see this type of drawing in 3400 or other courses. Okay, so I have this joint, and I have this velocity, and then this translational joint is moving toward this direction. And I would like to call Qi as the joint variable, which we already used that in the inverse and forward kinematics analysis. Okay, and Qi means the joint variable. Okay, and again, Qi equals to di or theta I. Okay, so di means it is a prismatic joint, which means it's a translational joint. Okay, and theta I means it is a revolute joint. Okay, revolute joint. Okay, so now the first case is a prismatic joint. Okay, so let me mark as P here. So for this case, what is the linear velocity? Okay, linear velocity I use as a vector, so the linear velocity equals to the velocity, the joint velocity, which is the Q dot, right? Because we call it Q as the joint variable, which is the position. And so Q dot means the velocity. Okay, and if we want to, because this is a vector, so we want to give a direction. So this is Q times K as a vector, and K is a unit vector. Means it is showing directions, okay? Okay, and how about the angular velocity? Okay, so the angular velocity, it is also a vector. For this case, there is no rotation, right? So the angular velocity equals to 0. Okay, how about a revolute joint? For a revolute joint, that is R, okay? And let me draw it this way. Assume that this is the rotating axis, and right here we have a revolute joint. and it is rotating, assume it's rotating around this direction. Okay, and this rotation theta is my qi, which is my joint variable. And then this revolute joint is connecting to a n effector. Okay, so this is, for example, this is a grasper. I draw it this way because this is a n effector. Okay, and the n effector is connecting to this revolute. Let me do the calculation of angular velocity first. Okay, so what is the angular velocity? The angular velocity is the q dot, which is the theta dot, right? Theta dot. And then that's it. And we should, since this is a vector, so we need to give a unit vector to show the direction. This is a unit vector, so it won't affect the absolute value. Okay? And so this only shows the direction. Okay, so obviously the angular velocity equals to theta dot, and we use a unified joint variable, which is q, so that we also write it as q dot. Okay, and then what is k in this case? Okay, so by definition, if this is a turning, and then the rotating axis using right-hand rule, that is the unit vector, and it is showing the direction. Okay, so again, we use right-hand rule, and please have your right hand, and then this can be this is my thumb, and these are the 4 fingers. Okay, so here it's pointing to the rotating positive rotating axis. Okay, and the rest of 4 fingers are along with the rotating direction. Okay, so then in this way we show the angular velocity. Okay, so then what is linear velocity of this point? Okay, assume that this link, this n effector link, and from the joint to the center of the n effector, we assume this is r. Okay, this is r. So what is the linear velocity? And the linear velocity, and if it is a vector, by definition, that is the angular velocity. Okay, so the angular velocity times this r, right? Okay, and the r means the rotating center to the point you want to calculate the linear velocity. Okay, and we use cross product. Okay, so the cross times the absolute r. Okay, and again, the dot product means this absolute value, which is the angular velocity, times the r times sine theta, sine the angle between the k and r, sine alpha. Okay, so the k and r, they're perpendicular to each other, then we will have sine theta, so that it directly equals to the omega times r. So that's why in most of the calculation we have the linear velocity equals to the angular velocity times r. Okay, so let's see another example that now we have 2 joints. We have 2 joints, and right here we have a revolute joint. Okay, so we have a revolute joint, and this is our rotating center. And the rotation, we call it, this is joint 1, so I call this Q1, okay, as the joint variable. And in this case, of course, it's theta 1. And this joint is connecting to a prismatic joint, And the prismatic joint, okay, so this is R and this is P, and the prismatic joint is connecting to a n effector, okay, so which is the tool. So here we have the tool. And this this prismatic joint and the joint variable, and which is d2, and so we called it q2 as the joint variable. Okay, so let me directly write q2. So what is the velocity of theta 1? So that is q1 dot. Okay, and what is the velocity of the prismatic joint? That is q2 dot. Again, q1 and q2 means position, and q1 dot and q2 dot means velocity. Okay, so now the 2-point velocity components are a function of joint variable and position. So now if we consider this case, and the 2-point velocity, which means the velocity of this and effector, this and effector, is a function of joint variables and joint, say joint velocity and positions. Okay, so what does it mean? It means joint velocity, that is q1 dot, q2 dot. And position means q1 and q2, which are the joint variable. Okay, so if we write it this way, so it will be the velocity, the 2-point velocity means, first of all, it is rotating. Okay, so think about, you have a robotic arm in the space, and anyway, your tooling gonna be rotate somehow. Okay, so when it is able to rotate, there's gonna be a angular velocity, and of course you can do translational motion of the tooling, so it means there's gonna be a linear velocity. Okay, so then what we are really interested in is the end effector's linear velocity and so what we're actually interested in is the angular velocity and the linear velocity of the end effector of this tool, right? We interested in this v, the linear velocity, and the angular velocity of the end effector. And again, these 2-point velocity, including the linear velocity and the angular velocity, is a function of both positions and velocities of all the joints. Okay, in this case, there are only 2 joints, so that's going to be q1, q2, q1 dot, and q2 dot. Okay, and mathematically, we can also write this way. That is the function of qi and qi dot. Okay, and qi means all the joints. Okay, it's easy to understand, right? And if you are controlling a robotic arm and it has multiple motors to control each joint, and so if you want to finally control the end effector's tooling's position and velocity, and now we're talking about velocity, so we want to control the end effector's velocity, the linear velocity and angular velocity. Of course, we need to know the joint velocity and the joint position of all the joints. Okay, so then let's start a new topic, that is the Jacobian. So what is that? So by definition, the Jacobian is a matrix for calculation. Okay? So simply speaking, it is a matrix for calculation. So what is this matrix? So the Jacobian is a matrix that is a function of point position that linearly relates the joint velocity to tool-point velocity. Okay? linearly relates the joint velocity to point velocity, to tool point velocity. Okay, so this is the definition of Jacobian. So it is a matrix, and this matrix is only a function of the position. It's not a function of velocity. So this Jacobian matrix is for calculation. It's for relating the end effector's velocity with the joint velocity. Okay, so if we write the mathematical equation, so that is the linear velocity and angular velocity of the end effector, that is the Jacobian matrix. It's able to be calculated by the Jacobian matrix linearly, and that is, here we have qi dot and q, and now we have two joints, so we have q1 dot and q2 dot, and this Jacobian matrix is a function of q1 and q2. Okay, so from this equation we can see that, okay, so if we want to calculate the end effector's velocity, if we are able to know the Jacobian matrix, and then we only need to know the velocity of the joints instead of the position. Okay, so we're just relating to velocity vectors. Okay, so it means if we know this Jacobian matrix, and that is great. So let's see how we're going to calculate this Jacobian. Okay, so from the rest of this lecture, we're going to talk about how to calculate this Jacobian matrix. And if we can know that, and then we're all set, because once we know this Jacobian matrix, and we can directly calculate the end effector's velocity. Okay, so now let's see the linear velocity. The linear velocity, v. Okay, so if we want to calculate the linear velocity v from this equation, so v equals 2, okay, so that is the first row, okay, so that should be another matrix. And this matrix, let me call it the Jacobian of v and times the vector of qi dot, q1 dot, and q2 dot in this case. Okay, so why is that? Okay, so let me show you the matrix operation that, okay, so here we have a v and we have a omega, and these are, these are two variables, okay, and I want to calculate these two, so assume that I have a matrix R11, R12, R21, and R22. And then I have the q1 dot and q2 dot. If we write the equation for that, what is that? It means v equals to, okay, so row times column, so that is R11 q1 dot plus R12 q2 dot. That's it, right? That's it. Okay, so this is the matrix multiplication. And now what is omega? Omega is in the second row, so it means we need to use the second row to do the calculation. Okay, so omega equals to R21. Okay, so this term times this term plus this term times this term. Okay, so that is R21 times q1 dot plus R22 times q2 dot. Okay, so that's it. So now it means we are able to put these things into this, and we can either use this format or we can use this format, and they are equivalent. Okay, and for our robotic calculation, normally we choose to use the matrix calculation. Okay. So it means if we want to calculate this JV, and what is JV if we want to use one matrix to consider this thing. So that is V equals to R11, R12, Q1 dot, and Q2 dot, right? Yeah, and that's correct. Okay, and how about the omega? So omega equals to R21, R22 times Q1 dot and Q2 dot. Okay, so this is our linear velocity Jacobian. Okay, and so this is called linear velocity Jacobian, JV. Okay, so then let's see what is that. And because in the definition, this is for calculation, right? And this Jacobian matrix is for calculation. And it is a function of the position only. Okay, so how we're going to achieve that? So then let's do one more thing. So since this is a linear velocity, it is more than one dimension. Okay, so say if we want to calculate the linear velocity, and say a 2 or n effector is moving in the space, and normally it can move in x and y and z, so it means this x is 3 elements. You need to have Vx, Vy, and Vz so that we're able to talk about the linear velocity. Okay, so Vx, by definition, that is the velocity along x-axis. So that is dx over dt. Okay, so then x is a function of both the two joint variables, because in this case, we assume that we only have two joints. So this dx over dt, that is the velocity, right? The velocity. So but it is a function of two joints. So if we want to calculate the differential, the partial differential, so that is equals to dx over dq1 and times dq1 over dt, so that we're able to find out the relationship between the end effector's position and the joint variable's velocity. Okay, so the end effector's velocity, sorry, this is the end effector's velocity. Okay, and plus dx over dq2 times dq2 over dt. Okay, so this is in x-axis. Okay, and again, your end effector can do 3-dimension x, y, z, so it can do 3-dimension translational motion. So it means my Vy, which is the velocity in the y-axis, the velocity of that, by definition, that is dy over dt, of course. Okay, and then that is dy, if we want to calculate the relationship with all the joints variables, so that is dy over dq1 times dq1 dt over dt plus dy over dq2 and dq2 over dt, and this is y. Okay, so now assume that we're just calculating 2 dimension, and of course in the real example you're going to calculate is 3 dimensions. So later I'm going to add that, but now for this simple question we assume that it is 2D question. Okay, so then we can see that what is J11 and J11, which is the elements of this and JV, which is the velocity, linear velocity Jacobian. So if it is the V, if it is 2-dimension means this linear velocity, it has x and y components. So now if we write the matrix, so that's going to be Vx, Vy equals to this linear velocity Jacobian, so that is something, and times the Q1 dot and Q2 dot. Okay, and the something should be J11, J12, and J21, and J22. Okay, and again, these two equations and this in matrix formatting, they should be equivalent. So it means my J11 equals 2. Okay, so this is Q1 dot, right? This is Q1 dot, so my J11 is dx over dq1, and my J12 equals to dx over dq2, and my J21 equals to dy over dq1, which is this term, and my J22 is this term. Okay, so that is dy over dq2. Okay, so this is my linear velocity Jacobian matrix, and that's it. So this is all from the definition. Okay, so then let's do one example. So this example, what we have is, again, this example, we go back to this two joint example, and now what we're talking about here is for a general two joint case. And now go back to this example that here we have a revolute joint, and then the revolute joint is connecting to a prismatic joint. Okay, and the prismatic joint is a P, here we have an R, and the prismatic joint is connecting to a and effector, okay? An and effector. And what we know is we know the joint variables, means we know the joint position and velocity for both. Okay, and for the first joint, that is Q1 and Q1 dot. Q1 means the theta 1, and Q1 dot means theta 1 dot, which is the velocity. Okay, and then my Q2, that is Q2 and Q2 dot. Okay, so for this example, we know that the end effector positions from forward kinematics are given by Qx equals to Q2 cosine Q1, and y equals to Q2 sine Q1. And Q1 in this case is theta 1, okay, and Q2 is this D2. Okay, and these two, they are calculated from the forward kinematics, means the DH convention, okay? So it means we already calculated, and we know that it is for these two. So the question is to find the linear velocity Jacobian. Okay, so if we want to find that, and again, we directly goes to this definition to do the calculation. So again, J11 equals to dx over dq1. So it means this dx over dq1. So we take a look at this term. So that is negative cosine q1 d cosine q1 d q over dq1. So that is negative q2 sine q1. Okay, and J12, that is dx over dq2, so that is sine q1. Okay, oh sorry, so J12 by definition, that is dx over dq2. So dx, again, we need to take a look at here, but we're doing dq2. So this term equals to cosine Q1. Okay, and J21, by definition, that is dy over dq1. So that is, we need to take a look at this term, and if it is dq1, and so that is q2 times cosine q1. And J22, by definition, that is dy over dq2. Again, we need to take a look at this y and dy over dq2, which is here, so it is linear. So if it is dq2, that is linear. So we have this term equals to sine q1. Okay, so we're all set. So then the linear velocity Jacobian matrix equals to negative q2 sine q1 and cosine q1, and this term is J21, so I just copy that. So this is q2 times cosine q1, and this term is this one, so that is sine q1. Okay. So this is the solution for this question, okay? Because we already know the x and y. So the next is the angular velocity. The angular velocity Jacobian. J omega. Okay, so if we take a look at the original equation we have, which is here, okay, so then we can see that over angular velocity equals to this term. Okay, so over angular velocity Jacobian matrix, by definition, that is the angular velocity equals to the angular velocity Jacobian times q1 dot and q2 dot. Because the definition of Jacobian is used for calculation, so it is relating the angular velocity and the joint velocity. Okay, so how about we go back to this question, for this question. So what is, example, for the above example, what is the angular velocity Jacobian? Okay, so if we take a look at this question, actually, we know that there is no linear velocity, so means q2 dot is 0. There is, okay, so q1 is a revolute joint, q2 is a prismatic joint, so q2 there is no angular velocity. Okay, so okay, so the angular velocity of the end effector, normally we're talking about the rotation around the base axis, okay? So it means we only have one angular velocity omega. It is different from x, y, and z of the translational motion. So this rotation, we only consider that with the base axis, okay? So it means we only have one line of that. So it means the angular velocity equals to J1 and J2 times Q1 dot and Q2 dot for this two joint case. Okay, and what is J2? J2, if we do the calculation, it means my omega equals to J1 times Q1 dot plus J2 times Q2 dot. Okay, and in this case, the end effector is angular velocity, and for the second joint, that is a prismatic joint, so it should be no effect on the final angular velocity. So it means my Q2 equals to 0. And so the angular velocity of the end effector is fully determined by the first joint, which is a revolute joint. So my J1 equals to 1. Okay, so it means for the simple case, we only have two joints, so the angular velocity Jacobian equals to 1, 0. Okay, so that's it. So then, what is after we talk about the linear velocity Jacobian and angular velocity Jacobian, which is JV and J omega. So what is the full manipulator Jacobian? So again, we call this matrix equation, so the linear velocity, and again, it could be xy or xyz, and depend on how many dimensions you want to calculate. Okay, and this is JQ1 and Q2 because the Jacobian is a matrix of only the joint position. Okay, and it's relating the effector's velocity and the joint velocity. Okay, so in this case, summarize that, we have x dot, y dot, and omega for this case. And then the full manipulator Jacobian, it should be JV and J omega. Okay, we directly write down that. Okay, so then we just copy from the previous calculation, which is here and here. So then we directly have the full manipulator Jacobian, so that is negative Q2 times sine Q1, and this term is cosine Q1, and this term is Q2 times cosine Q1, and here this term is sine Q1, and this is 1 and this is 0, and times Q1 dot and Q2 dot. Real number question, and to see how to apply it. Okay, so we're still using this example from the previous calculation. Okay, so now from the previous calculation, and which in this case we have one is the revolute joint and prismatic joint, and we already calculate the linear velocity Jacobian and angular velocity Jacobian already by the definition. Okay, so now in this real number question, we know that the joint 2 is extended 0.5 meter. And the extending speed is 1 meter per second. Okay, and we want to, and the joint 2 and the joint 1 is rotating, which is this thing is rotating at 2 radius per second. So the question is to find n-tool's linear and angular velocity. Okay, so which is common, right? Means we already know the joints. Okay, so means we know the joints variable. Okay, so it means we know the joint variables, means we know the joint position and velocity, and we want to calculate the end effector's velocity. Okay, and now we know these real numbers, and so we can start to calculate. Okay, so with this description, and let me write down these variables. So what is Q1? Okay, Q1 is 0, and we assume that it is at the original position, and Q1 dot is 2 radius per second. And Q2 is the position, so Q2 extended 0.5 meters, so Q2 is 0.5. And Q2 dot is the velocity of this joint, so that is 1 meter per second, which is right here, so that is 1. Okay, so then what is the end tool's linear velocity and angular velocity? Okay, so if we want to calculate that, and for the linear velocity, because it's 2D, so there is an x and y, means we have the linear velocity in the x-axis and linear velocity in the y-axis, as well as the angular velocity omega. Okay, And from the previous calculation, which is here, and we would like to directly use that. So this is over Jacobian matrix, and which is the full manipulator Jacobian matrix, and times the Q1 dot and Q2 dot. So now we know Q1 dot is 2 and Q2 dot is 1. Okay, so which is given. For this Jacobian matrix, and we already know these terms, so we can do a quick calculation. So the first row, the first term, that is negative Q2 times sine Q1, and Q1 is 0, so this is 0, and this term is cosine Q1, okay, so which is right here, cosine Q1, and so for cosine Q1, and Q1 is 0, so cosine Q1 equals to 1. And Q2, the second row is Q2 times cosine Q1, and Q2 is 0.5 times Q1, cosine Q1 is 1, so that is 0.5. And the next term is sine Q1, so we have sine Q1, and Q1 is 0, so this is 0. Okay, so then the last row, which is for the angular velocity Jacobian, that is 1, 0. We already know that. Okay, and then we just give these real numbers from these given joint variables. So this is 0.5 and this is 0. Okay, and then we do the calculation of this matrix multiply this matrix. Okay, so then we do the matrix multiplication. So then the first term is the first row times this vector, so that is 1. Okay, and the second term is this row, the second row times the vector, so that is 2 times 0.5 plus 0 times 1, so that is 1. Okay, and the last row is 2. Okay, because this is 0, so that is 1, 1, 2. Okay, so it means that to answer the question, the end effectors, the end tools, linear and angular velocity, so it means the end effector, it is on the along x-axis, the velocity is 1 meter per second. And along y-axis, the linear velocity is 1 meter per second, because this is x dot and this is y dot. And the angular velocity, which is 2 radians per second. Okay. So that is all for today.